And the first speaker is Natalia Berloff from the University of Cambridge, who is going to talk about game-based interpreting with color, light, and texture.
Okay, thank you. And I also would like to start by thanking the organizers for such an interesting meeting and for having it in such a spectacular location. So I'm Natalia Berloff. I lead the quantum fluids at the University of Cambridge, and the subgroup of this group actually does pi computing, which stands for physics-inspired computing. And we are part of this European consortium called Heisenberg, where we're trying to implement the concepts of the quantum-based computing in the real systems. So when you talk about unconventional computer, you have to start with a motivational slide showing the violation of different scaling laws, of course, Leonard Keynes law, etc. But I just would like to say that indeed the demands are growing, and to meet this increased demand in computer power, we have to now spend exponentially increasing costs. Therefore, there are two ways out of it: either to come up with a more efficient algorithms, kind of incremental steps, and I think we already mostly exhausted this path, or come up with alternative hardware that can do this analog computing, so to replace the whole concept of von Neumann architecture. And indeed, this is everything in cycles in this world. So in 40s, 50s, and 60s, the analog computer dominated, simply stirring from the fact that electric circuits obey differential equations. So to simulate the differential equations, you can use electrical circuits. For the last 70 years, we really entertain this, and our advances are connected to the progression that digital computers with their von Neumann architecture that separate memory from the computation. And in the last 30 years, we have the most interesting idea was quantum computers, the idea that challenged the digital classical computers with its entanglement, quantum gates, and quantum tunneling. However, in the last maybe 10 years, we can see that actually this route doesn't yield any fruit. So perhaps we have to look elsewhere, not necessarily quantum, not necessarily entanglement, but simply use the physics and its inherent parallelism, its inherent ability to actually do a lot of computation for us. And one example is perhaps neuromorphic computers, reservoir engineering, and I will talk about this new concept called gate-based computing. So the idea behind this nature is very good at optimizing. Actually, physical systems follow different principles, minimize different quantities, action, time, energy, curvature, dissipation. And so if you find a way of mapping an interesting computational problem onto these quantities and then arrange the system with enough knobs to turn, to control, then the system may find a solution for you. And this is an example. This is an actual physical system. This is in collaboration with a group of Professor Pavlos Lagoudakis from Southampton and Skoltech that we did a few years back. So what you will see in this video, there are two panels, momentum and real space. And you will see the formation of the lattice of polariton condensates from the pulsed excitation. So there is a pulse, the huge reservoir of dark states is created, and then the system relaxes into the lattice of 100 condensates. And as the reservoir winds its number of particles, the system decays, but it will rearrange in the course of this movie 3 times to arrange the particular phase configuration. So 3 times in the duration of this movie, you will see the formation of the coherent state. So in experiment, it takes about 100 picoseconds. So in 100 picoseconds, this system is going to solve a rather hard problem that would take very long to solve on the classical computer. So there is a pulse, no coherence so far, and then coherence is formed. You can see the clear Bragg peaks on the momentum image, and you can see the clear lattice. And then it breaks down again, no coherence here. rearrange it again, and there are 3 times it does so, each time with its own different phase configuration across the entire condensate. Okay, so it solved a very difficult problem. Supremacy has been established, but this is not an interesting problem for us. It's not a practical problem. It's not a problem that we can control. It's just hardware. This physical system did a miracle, but it's not useful. So ideally, what we would like to have is we would like to start with a real-life problem and then map it onto the graph geometry. Nodes are variables, and then we have some connections, some coupling strength between the nodes. So in other words, we would like to map this problem onto a particular spin Hamiltonian. It would be XY, Ising, ports, k-clock, k-local, etc., and then run the system that actually naturally minimizes the particular spin Hamiltonian. So this is mathematically rigorous fact that any problem, vaguely speaking, any problem can be mapped with just polynomial overhead onto the minimization of the spin Hamiltonian. And again, mathematically, we start with function f of many variables x, then we map these variables into phases, and then we would like to minimize, let's say, this Hamiltonian, which is an xy classical xy Hamiltonian if phases are continuous. Ising if phases take 2 values, 0, pi, or ports of k-clock, so any discrete number of states. So the structure in this concept, the structure of the function is fully mapped, fully represented by the coupling strength Jij. Okay, and then we can think of 2 approaches to build the physics-based hardware. In one, the dynamics is physically driven. The system minimizes whatever this principle that I mentioned before, but then for us, it's an engineering challenge to create the pairwise coupling between the elements. That's usually hard. Another concept that other people followed is when you think of the particular physics and can use the physical system to implement the couplings, and then the dynamics that mimics the operation of the physical system is introduced as a feedback mechanism. And there are many now, it's very fruitful area of research where different systems are used to implement either of these 2 approaches. And my group participated in actually this lower row of the machines. So we collaborated with Microsoft Cambridge in creation analog iterative machine. As a part of the Heisenberg that I mentioned, we worked with spatial photonic Ising machine. And then with Lars English from Dixon University, we had subharmonic resonators implemented. But for and there is a different story behind different machine and different challenges. But today I'll touch upon polariton condensates. Okay, so what is gain-based computer? What is the main principle? So gain-based, because we map our problem onto the gain and loss rates of a driven dissipative system. We need light coupled to matter because light gives parallelism and speed, where matter gives nonlinearity, control, and energy efficiency. Okay, then that's the diagram that shows why we really find the meaning. So we start with vacuum. This is driven dissipative system. It does not exist without the gain. And then we start ramping up the gain, so populating the physical nodes. So the physical nodes grow. Initially, the loss function, because it depends itself on this mode, is just flat. But then as the time goes on, as the physical nodes gets more and more excited, it acquires the shape of the function that we would like to minimize. And sooner or later, these 2 meet. As you can see, we approach this function from below. These 2 meet, and this is where the mode selection takes place. Because at this particular moment, for this particular mode, the coherence can be established. There is enough modes to have the coherence across the system. And here we have the macroscopic signal, and here we have light. Actually, our coherence establishes in this light matter system as we can see it. So the line shines at this configuration, and we have our minimum. Then we simply read out this particular mode as the answer to our problem. So there are these important ingredients. This is a dynamical system. They have to be coherence established. There is this bifurcation, so symmetry breaking mechanism, and the fact that we have the loss function that actually itself depends on these modes. Okay, so how does it work and where do we get these losses and how we mathematically represent them and how these elements play together? So we deal with a complex system. So as we start with the system that is described by the complex order parameter wave function, we can actually integrate out in a tight binding approximation the spatial degrees of freedom. So each element will be described by the complex function of time only, this psi I. And then we set up the dynamical evolution, because this is what the physical system does. After the tight binding approximation, we write our equation Ginzburg-Landau or Stewart-Landau or Ross-Vitaevsky, but in this case, it'll be more Stewart-Landau networks because it's a dynamical evolution that minimizes the functional of losses. So how the losses look like? So depending on the system, so our polaritonic system actually minimizes the losses that contain these terms. So the first term just depends on each individual element, and this is responsible for the symmetry breaking. So how this term, so gamma here is an effective gain. It can be negative if losses overcome the pump. So we start with negative gamma. So the first part of this loss potential is a convex function, a quartic. So the node, all the modes sit comfortably at the zero, the vacuum state. As the gain increases, so as gamma increases, we have the bifurcation, the whole bifurcation, and now the system can take any value along the ring with a radius square root of gamma, right? But which particular phase it takes depends now on the minimum of this part of the loss function, which for equal amplitude, with amplitude given square root of gamma, reduces to the minimizing xy Hamiltonian. To minimize the classical Ising-Hamiltonian, we need to take the same equation, the same losses, the same system, but now introduce the second order resonance. So in other words, with non-resonant term combined with the resonant term, fixes the phases to 0 and pi, and therefore the minimum of the Ising-Hamiltonian is realized. We can go further and actually also show that in sufficiently large PAM, we can also minimize the k-local Hamiltonian, in which case the elements of the system, this individual condensates, let's say oscillator centers, interact with the tensors. Okay, so this is the mathematical basis of it, but the story doesn't end here. But let me just take maybe a few words about polariton condensates and how this process of getting the polariton condensate evolved. I don't think for this audience I have to give an introduction for polaritons, and I have two great speakers after me also talking about polariton condensates. I'll just remind you that these polariton condensates come from hybridization of photon and exciton in semiconductor microcavity. They can Bose-Einstein condense. And so with a spatial light modulator, for instance, you can create a lattice of polariton condensates in any geometry. And there are many beautiful properties of the system, a lot of parameters to vary depending on the sample. You can have short-lived or long-lived condensates. You can change the coherence length, etc., etc. They can be at 5 Kelvin or at room temperature. And in the course of the last maybe 12 years, actually, we collaborated with many experimental groups trying to implement the concept of gain computing in hardware. So the first work started, of course, in Cambridge with Jeremy Baumberg and Nanophotonics Center, where we studied the lattices of the condensates and established actually that the condensates can talk on large distances. The size of the individual condensate about 2 microns, but they can feel each other on the length of 100, 150 microns. So really there is this long range interactions that can be established. Then in another group of Professor Pavlos Lagoudakis, we actually look in more detail of how the interaction strength changes between the two condensates as you change the distance between them or the pumping parameters or the profile of the condensate itself. So you can show that you can establish the coupling strength varying in size and in magnitude, and then realize the concept of the polariton simulator. With Jacqueline Bloch and Alberto Amo, we look at the problem of actually making the pairwise interactions possible, but that was a theoretical work, and we couldn't do it, for the experiment, the condensates were too short-lived, too short of the coherence lengths to actually implement these couplings reliably. Next thing took us to the group of Wei Bao and Wassenaar University. In the latest work, we implemented these XY Hamiltonians and the room temperature organic, inorganic halide perovskites lattices. And there is another group now in St. Andrews, Hamid Al-Hadi, with whom we try now to use waveguides to have these pairwise interactions. So at this moment, I think it feels that the main challenge and the main task now lies in experimental realization. We need to have these controllable pairwise interactions between any condensates, between any oscillatory sites in our system. But actually, the main challenge comes from the theoretical understanding of what actually do we have to implement in our system. Which control do we require, and which properties of the systems would actually lead to the global rather than the local minimum? This is a big problem. And actually, you can also think it from the perspective of once we understand what do we need from the physical system, we can implement this behavior of the physical system as a feedback in other systems to also have this the optimal search for the solution. So now let me take you through the very simple problem just to give you an idea of kind of what are the challenges on this route. So how do we actually devise the system to guarantee that it finds the lower ground state, the minimum? So when it doesn't work, so I'll give you a very small example of the challenge that lies beneath. So I have to say again that this is the time when there are a lot of machines, XY machine, Q clock machine comes your way based on very different physical systems, from spinor systems to surface acoustic waves to solid state, etc., etc. And then they use, to show the capability of their machine, they use a large number of spins. And then they show, that's the method, that classical method that gives you worse result than what we do with our machine. So to those people, I suggest, okay, forget about 200 and 1,000 nodes, have 8. So, and let's start with an Ising model, the simplest model you can think of. So we are minimizing this Hamiltonian, where Si as j is plus or minus 1, it's classical. So, and then I will take for this, so for my computer, for my physically inspired computing, actually, because the phase is now fixed to 0 and pi, my model has the real parameters, right? Because the argument is now 0 and pi. So instead of this complex function, I have real function x, okay? And the couplings that I suggest, so you have just 8 and equal 8. And then you have antiferromagnetic couplings along the ring. So this is Möbius-like geometry. And then you have antiferromagnetic coupling between the elements across the ring. And this is the coupling that you vary. This is J. Okay. So if J is small, say 0, then antiferromagnetic links, of course, would like the system to have the spins in opposite direction to minimize XY, to minimize the Ising Hamiltonian, right? So if J is small, then you expect that there is that the system simply neglects that it violates the coupling across the ring, they're small, and therefore just establishes itself in alternating plus and minus position. However, as J grows, then these links become significant. So instead, the system decides to violate just 2 links on the opposite sides of the Möbius ladder graph. Okay. And so if I look at this J, so there is this critical value, 1/2, when the energies of this S0 and S1 states are the same. And the global minimum of the Ising Hamiltonian on the right is this one, S1. On the left, it should be this, S0. However, there is another critical value, this JE, This is where the principal eigenvector sign changed. So the principal eigenvector of the matrix actually tells me where the system goes initially, where the symmetry breaking takes it. So at this point, the primary eigenvector on the left is the same as the signs of S0, but on the right, it's S1. And so if I use my gain-based computing, let me call it generally the coherent Ising machine, just to put all of this under the same umbrella, it doesn't mean which one I have, then my machine will perform extremely poorly in this region. And the reason is that as you think of this very simple configuration, but to going from one to another, it's not enough to flip one spin. I have to flip half of the spins in the system. So this is what happened in the soft amplitude machine with the continuous variables. It follows a particular path, which is actually the global minimum for this system at that for these amplitudes. And then the amplitudes grow, but it's already too late to actually do the bifurcation because the barriers become prohibitively high. Okay, so very bad for this region. And then I asked the group of Johan Ackermann, with whom we talked about, they implemented this surface acoustic wave. And I said, okay, again, forget about large N, let's do 8. So they run, and indeed, so just focus on this pink region. They actually even don't do that well in this region because this machine does extremely well in the easy parts and then drops significantly to the success probability about 1/5, was worse than even the gradient descent. And actually they showed, yes, their machine has exactly the same behavior. Okay, so what can we do? Very bad for the continuous amplitudes for this simple problem. The problem is clear, it will occur for other problems as well. So the first attempt that we took, we introduced this manifold reduction technique. So we said the problem is, actually in this case, the problem is that the system with the soft amplitudes, it can sacrifice the amplitudes of those elements along which they sacrifice this antiferromagnetic coupling. And therefore, that becomes the new global minimum, the wrong global minimum. Okay. So what if we prevent systems from doing that? So in other words, we restrict the amplitude. We still allow to do symmetry breaking bifurcation. They still bifurcate from 0, but we don't allow them to deviate too much. So we keep them on this restricted manifold, continuously adjusting them towards the same average state. And actually that increases the success probability dramatically to around more than 60%. Also, but I need to say that we know that the ground truth, for instance, the quantum annealing here implemented using the transverse field Ising model actually performs very well. It drops here simply because it depends on the annealing time, which depends on the gap. And at this line, the energy gap disappears. So it does poorly in here, but again, if you take longer annealing schedule, you'll do slightly better there. But our method is insensitive to the gap. It stays about the same and then jumps back to the 100%. But that's not good enough. And so then it took us to the concept of vector Ising spin annealer. So in this case, we represent each spin as actually 3 Ising spins, right? So each component is Ising spin itself, but it's a soft mode Ising spin. And then our Hamiltonian that we minimize, or actually this free energy, free loss functional that we have consists of 3 terms. So one term is as before, gives us symmetry breaking for the modulus of the vector. The second one is that like the Ising spin, but it has the dot product between the vectors. It coincides with the Ising part if these 2 vectors are collinear. And to make them collinear at the end of the annealing process, we introduce this vector product that actually penalizes for vectors not to be collinear. But the strength of this term just grows with time. So that gives us this kind of the analog of the Stewart-Landau network, but with slightly with these cubic terms that actually could also be brought as a quadratic terms by using Rosenblatt polynomials. But anyway, so then you start with the vacuum state, and now you can visualize it even on a Bloch sphere. It bifurcates, and then the system goes in different ways, exploits in this three-dimensional space, and at the end, all vectors become collinear in the direction they spontaneously choose. I do not force any potential direction. And that brings, even in this very simple implementation, we kept everything, initial states all the same, it actually brings back to almost more than 80–90% of the success. Okay, so what is the reason for that? Because if we have a scalar system, then after the bifurcation, it takes very long barriers to actually flip the spins all the way to the opposite sign, but the same in amplitude, whereas in 3 dimensions, that's much easier. The system can rotate and then go on another side without large barrier preventing them to do so. So the dimension 3 is a crucial dimension. It's very similar to when we have the condensation, let's say, and this is from our old work with Boris Svistanov, when we have the condensation of the waves, and then in 3D, you always have the vortex tangle that actually annihilate the vortices at the end of the simulation. And in 2D, you have KT physics, that long range vortices actually can stay in the system for a very long time. Okay, so I'm almost finished. So again, we have a lot of theoretical challenges. So I listed just maybe 4 of those. First, it's an interesting problem because each computational optimization combinatorial problem has its own landscape that's defined by this coupling JIJ. So it's interesting how to connect the evolution of the system and how to get rid of the excitation, such as the vortex rings or the defects on this in this spin glass, but governed by the interactions given from the problem. So soft spin Hamiltonians and beyond, we also look at extending degrees of freedom using all degrees of freedom, not just the phases, but the amplitudes. It's unclear question how the quantum effects, what is the role of the quantum effects? Because before the condensation, in our polariton condensate, the system is fully quantum. So how quantum statistics actually assist in finding the low energy state? And then we look at various artificial intelligence application and, from the point of view of dense associative memory, generative diffusion models, and how to use these systems for inference and classification. Okay, and I finish. So there's other aspects of our work, but I would like to finish by acknowledging my group. So you've seen the work of Kirill Kalinin, just recent PhD student who's now already staff at Microsoft Cambridge, also former PhD student and postdoc Nikita Stroyev, and current PhD student James Cummings and Marvin Sayed. So thank you.
Is there any question?
No, thank you very much. You said that your polaritons are onto, but they are stationary states of gain and loss.
Oh, yeah.
Very large.
Yeah. No. I said, so when the coherence is established, then the system becomes semi-classical, right? But on the route to that stationary state, it's quantum statistics, right? So we expect that this is, and while you have few, because you start with a vacuum, you have no particles, and then you ramp up the gain. You have just few polaritons, quantum effects, perhaps entanglement, the more and more. When the coherence establishes, that's it. You have classical system, semi-classical system. So in my view, it's very similar to what we have in quantum systems per se. Once you measure, it became classical. So the establishment of the coherence, that's the class. Your result is classical result. But on the route to that classical result, there are quantum effects.
Right.
Yeah,
And energy cavity is also classical. In some sense, but classifications are classical. So in that sense, why do you need quantum fluctuations to understand?
I mean, if you start with the full quantum equations, you can follow these quantum trajectories of polariton particles, right? If you have only, handful of polartons, they behave as quantum particles.
Right, and then in this new particle limits, then we
Yes, and that's how you start. So that's what I'm saying. When you establish the coherence, when the coherence is established, that's classical, no questions, and you have large occupations, etc. On the root, because you see it's a dynamical system, so whether or not the system finds the global minimum depends on its basin of attraction, right? So you start with kind of random noise, some fluctuations and everything. But where you start and whether the system is capable of actually jumping to a different basin of attraction, whether it's actually capable of exploring this larger Hilbert space, this is quite possible that the dynamical behavior of the system with the quantum effects would be different from the pure classical system. But you're absolutely right. At the end, it's a classical, or even when you already have macroscopic occupation, more or less, that's already becomes classical. But I'm talking about really just the first stages that perhaps it still needs to be established, allows us to jump to change the basin of attraction on the route as the system navigates the route to this global minimum. But this is very important. This is a very important question, and we're trying to show it's rigorously, what really helps and how.
I was wondering whether there is a concept of electricity in these systems, like the same equivalent of the radioactive
Quantum.
device.
The principle is different in the sense that, because if you look at the quantum annealing, adiabaticity of quantum annealing, so you're saying, you prepare the state where you're in the ground state, and then you adiabatically change your Hamiltonian until it reaches the shape of the Hamiltonian that you would like to minimize. And you have to do it sufficiently slow, and how slow you do should depend on the spectral gap, so the distance between your ground and the first excited state. This principle has some similarity that you do have the annealing terms there, because you anneal the gain, and you also have this modification of the function that you have. But if I take you back, so you see, so this is what I depicted here. In the quantum annealing case, you would already be here, and then you would follow this trajectory down, and you will stay at this always formed minimum. In our case, the system is different because we don't stay there. We occupy the modes, and we really approach this landscape from below. It's a fundamentally different concept. You are not on the top of this landscape and always remain in the global minimum. You don't. Global minimum of this loss function is irrelevant until these two processes came together and the lasing, this mode selection occurred. So it's a different process that is not a diabetic quantum annealing. But there is an annealing concept that, you ramp up the gain, in a sense, and it has to be sufficiently slow, but it's not relevant to the gap. As you can see, it's insensitive to the gap.
Thank you.